Okay, so last video we talked a little bit about the convergence of sequence, and we defined the convergence of sequences, and we talked about series and how series can be defined as a sequence of partial sums. And we literally just got a bunch of definitions down. We also talked about the density of Q and R, I think, but the primary purpose of that video was to get those definitions down. I wanted to give an example in this video, just a really basic one, of proving the convergence of a very basic sequence that we used a lot in high school, or at least I used a lot in high school. And it's the one that the sequence A of n being defined as being 1 over n, as n gets really big, converges to 0. And that was pretty much the main way in high school that I did limits. So I thought it would be a nice one to prove, and it's a fairly easy one to prove. So to start off, I'll give myself a little bit more space, but to start off, we're going to, I'll just remind you, if we're trying to prove a sequence converges to a particular value, we're wanting to prove that there is a number, which we usually call capital N, such that beyond that point, every number in the sequence is within a certain distance of our, what we're calling the limiting point, given a specific epsilon as our distance, and we can decide an n from that. So what we're going to do is we're going to choose our capital N to be equal to 1 over epsilon, and for all n being larger than n, so for all n being larger than capital N, n is greater than 1 over epsilon. And what we can do is we can flip our inequality around using our properties of order. So that means that 1 over n is less than epsilon, and we can rewrite that as 1 over n minus 0 is less than epsilon, which means by our definition of convergence, our sequence A of n converges to 0, which is that value there. So really, really simply done. We picked a particular value and we showed that everything beyond that point, given some epsilon being arbitrary, everything beyond capital N will lie within a particular distance of this 0. Which is our convergence point. So that's basically it. We've shown that 1 over n, as n gets really large, converges to 0. So that's quite a good example. It is, as I said, it's quite a typical convergence that we use a lot in high school with limits. So that's quite a nice proof. It's a very simple proof, and it's a proof of a sequence that we used quite a lot in high school. Or at least, as I said, I used quite a lot in high school. So now I wanted to talk about the uniqueness of limits. And basically that's just saying that for any sequence that converges, it only converges to one value. It doesn't converge to multiple values. And the way we're going to go about doing that, as I'll write this in a different colour, is we are going to, just for starters, we'll assume that our sequence converges for A, and we'll assume that our sequence converges to B. And what we're going to do is we're going to argue that A and B are the same thing. So rewriting our definition of convergence, that means that A of n minus A is less than epsilon for all n being greater than capital N, where epsilon is arbitrary and n is determined from it. And again, essentially writing the same thing out again, A of n minus B is also, we can choose epsilon because epsilon's arbitrary, we can choose it to be the same, and perhaps, just for the sake of it, we'll say it's a different number. And then, because we've said it's a different number, we'll just let P be equal to the max of the two numbers. All right. What we can now do is, if we call this statement 1 and we call this statement 2, we can rewrite statement 1 as negative epsilon is less than A minus AN is less than epsilon, and we can rewrite statement 2 as negative epsilon is less than AN minus B, which is less than epsilon. And that's quite a basic property of, what are they called? Of absolute values. So, if the absolute value is less than 3, then that just means it's between -3 and 3. Taking the sum of these two inequalities gives us -2 epsilon is less than, a minus b, and that just cancels out with that. A minus b is less than 2 epsilon, which is essentially the same thing as a minus b is less than 2 epsilon, or the absolute value of it. And that essentially completes the proof. Because it means, you could sort of say that means that A converges to B, because this is essentially our definition of convergence, except we're ignoring this sort of whole thing to do with N and M. Hold up, sorry, quick adjustment. The proof's not really altered that much, but that was supposed to be a P, because we wanted the same indices so we could add them, and that was supposed to be an M. But you get the idea. I'm not trying to be super formal. I'll write this up properly on the handout. But yeah, so A and B converge to the same point. A converges to B. The difference between A and B can be made arbitrarily small, however you want to argue it. That means that A is equal to B. No real other way that this statement can be true for any arbitrary epsilon. Of course, if it was a specified epsilon, then we could say it's true, but because it's arbitrary, it must be that A is equal to B. And that's the uniqueness of limits. It's a little theorem. I just wanted to point it out at the beginning because, of course, if we had, non-uniqueness of limits, then we would have to account for that and talk about that later on. But they're unique, so that's pretty handy. A couple definitions and a couple of theorems we'll be going through. Now, definition number 1, as you can see, it's written there. A of n is bounded if the absolute value of A of n is less than some number. I called it capital A, for whatever A is, and that has to be true for every single number in the series. So take the series, say an is equal to 1, 2, 2, 2 forever, then A of n is bounded because it never goes beyond 2 and it never goes beneath 1. So its absolute value never exceeds a particular value of 10 or 20 or 30, whatever it is, there is a sort of particular point that it doesn't go beyond. Whereas the sequence A of n, 1, 2, 3, 4, etc., that isn't bounded. It's bounded below, as in it never goes below a certain point, but it's not bounded above in the sense that if I said that the upper bound was 30, well, I can show that 31 is part of it. So I've shown it's not bounded. And the reason why I bring this idea of boundedness of a sequence up is because all convergent sequences are bounded. And that is going to be fairly important. I'm not actually going to prove that because I think that is fairly intuitive. So I'm not going to prove that because I think that's quite intuitive. It's just... So I'm not going to prove that, and the reason being is that I think this is quite intuitive with what we know about the real numbers. And it's not necessarily the case for all number systems. I'm sure there is some number system where you can have an a convergent sequence that isn't bounded. But when we're dealing explicitly with real numbers, it has to be the case. And that's because if it's bounded, then we know the trailing terms have to be within some distance of, A. And then the only terms that could be unbounded are the terms sort of towards the beginning, but they have to be numbers. That's the thing about real analysis, is we're dealing with numbers. Infinity isn't a number, which means everything's going to be less than infinity, which means it's bounded. So that's a pretty easy theorem, this one here. So I decided not to write the proof. I think in the handout I might walk through a proof as an exercise because it is, as I said, it's not hugely difficult to do, but it's a nice activity. The next theorem I wanted to prove is the algebraic limit theorem. So I'll state what it is first, of course. The algebraic limit theorem it's a set of algebraic stuff, so manipulations, that we can do to convergent sequences. and there's a couple properties. The first property of the algebraic limit theorem is, so we're working with A of n converges to A and B of n converges to B. So the limit of C times A of n is going to be equal to C times A. Makes sense, hopefully. The next one is that the limit of A of n plus B of n is equal to A plus B. The next one is the limit of A of n times B of n is equal to A times B. And then there should be another I there. The last one is division. Probably could have guessed that, but A of n over B of n is equal to A over B, with B not being equal to 0. Basic algebra. Algebraic properties, not algebra as in abstract algebra, algebra as in like addition, multiplication, stuff like that. And that's really nice, because that means if we've got two sequences and we know what they converge to, then we can figure out what their sum or their product or their quotient or their difference or whatever converges to. Essentially, there are differences in these proofs. I'll prove the first one, but they are essentially just the same thing. We'll prove this guy, number I. So if the limit of C of A of n converges to CA, that is essentially the same, writing out a definition, as saying CA of n minus CA is less than epsilon, for epsilon being arbitrary. Properties of absolute values, we can pull out the C, and we've got C of A of n is less than epsilon. So this is what we're trying to prove here, this guy. If we can prove that, we've proven part I. And that's really easy to prove, because we've assumed that A of n converges. So if A of n converges to A, which we're stating that it does, that means that A of n minus A is less than eta. I'm using a different variable than epsilon, but it's the same idea. And then if I choose eta to be equal to epsilon over the magnitude of C, then we can say, because A of n converges, then A of n must be less than epsilon on the magnitude of C, multiplying across, and we get magnitude, absolute value of C, A of n minus A is less than epsilon, which is this guy up here that we wanted to prove. Pretty basic. The other ones are similar. There's some stuff that comes into play, so I'll leave them in the handout, or I might leave them as exercises in the handout with some guidance, because they're a similar idea. They're not hugely difficult to prove, but they're very powerful when dealing with limits. Another really powerful property is the ordered limit theorem. Again, it's broken up into a few parts. The first part is if A of n is greater than 0, if all numbers in the sequence are greater than 0, then it converges to a number greater than 0. If all the numbers in a sequence are less than all the numbers in a different sequence, then the thing that the first sequence converges to is less than the thing that the second sequence converges to. And the last one, which is basically just the first one but a little bit more general, is that if all the numbers in a sequence are greater than a particular value, then what that sequence converges to is greater than that same value, which we called C. Or the other one is if all the numbers in the sequence are less than or equal to a particular value, then we know that whatever that converges to is less than said value, that value of C. So if all the terms in a sequence are greater than 0, then it probably converges, or it does converge to something greater than 0. If all the terms in a sequence are less than all the other terms in a sequence, then the first sequence converges to a value less than the second sequence. And then this third property here, which is a bit hard to say, I'll be honest, but just if everything in a sequence is larger than a particular value, then it converges to something larger than, or same deal but with smaller than. I'll prove just the first one, again, same reasons as above, because the other ones are fairly similar. So to prove the first one, we'll actually do a contradiction, so I'll write that up the top just to remind you. We're going to be using a proof by contradiction. So suppose that A is less than 0. And now if we choose epsilon to be equal to the absolute value of A, then because we know by the definition of convergence that an minus A has to be less than any arbitrarily chosen epsilon, we can decide that it's less than magnitude of A, given a particular value of n, given a large enough value of n. And now if we just choose one of those values of n, which we call sort of like the first value of n, capital N, an minus A is less than the absolute value of A. All I've done between these two steps is in this second step here, n was arbitrary, but larger than a particular value, and here that's that particular value that it has to be larger than. It's just from our definition. All that this says in the end is that A sub capital N has to be less than 0. And that's because if it was greater than 0, this thing wouldn't work out. This inequality up here wouldn't work out. Again, basic properties of inequalities. All right, so hopefully that was fairly easy to go through, and the other ones are similar. You just set it up, and a contradiction works really, really well for this sort of inequality type proof. The next one we're going to look at is the definition of increasing. A sequence is increasing. Sorry, why did I write function? That's bizarre. Let me change that. So the next thing I want to do is define increasing, decreasing, and monotone so that we can look in a second at the monotone convergence theorem. So a sequence is increasing if A of n plus 1 is greater than A of n, greater than or equal to, and it's decreasing if A of n plus 1 is less than or equal to A of n. So increasing if the successive terms are larger than the previous terms, and decreasing if the successive terms are smaller than the previous terms. And it's called monotone if it's either increasing or decreasing. So that's the same as when we learnt about functions in high school, well, pretty much. So the monotone convergence theorem, it's a nice name, is just saying that if a sequence is monotone and bounded above, it has to converge. And the proof of that is actually quite nice and unique-ish to real numbers. So we'll start going through it. I'll go through it in white. It seems reasonable. If you were to just think about it on a number line, say, just to try and get our heads around it, say this is our convergence point. If it's increasing, each successive term has to be after the last. And if it's bounded above, that means it can't go below, it can't go above whatever our bound is. We're looking at, I should probably have specified, we're just going to prove the case when it's increasing. I'll leave proving the case where it's decreasing to you if you want to. It is almost identical, so it's kind of unnecessary that we prove it here. But if a sequence is increasing and it's bounded above, then it seems reasonable to think that the value that it converges to, this value of A that it converges to, would be the supremum of the sequence. I'm going to rewrite this as an S just because that's how I have it in my notes. And now we're going to prove it. So we're actually kind of proving something a little bit stronger than the monotone convergence theorem. We're proving that if a sequence is monotone and bounded, it converges to the supremum of the sequence. So the proof is as follows. We know by the definition of the supremum that S minus epsilon is not going to be an upper bound, which means that some point in our sequence, because of the supremum, S minus epsilon has to be less than that point. Otherwise, it would be a least upper bound, and then S wouldn't have been the supremum, which is, of course, a contradiction. Because our sequence is increasing, we know each successive term for n being greater than n, that a of n is going to be less than or equal to, a of capital, a of capital N is going to be less than or equal to a of little n, which means we can write out that S minus epsilon, which we've said is less than an because it's a supremum, really getting my capitals wrong today, an is less than or equal to an, and we know because it's a supremum that has to be less than S. Probably should put my equal signs on. And that S is going to be less than S plus epsilon, right? So ignoring this part of it, we can subtract S from both sides and we get negative epsilon is less than an minus S is less than epsilon for all n being larger than our capital N, which is just the same as saying an minus S, absolute value of that, is less than epsilon. For arbitrary epsilon, we can find an n, which is the exact definition of the convergence of a sequence. So that's great. We've proven the monotone convergence theorem, and it is an incredibly powerful theorem. And we're going to look at an exact example of just how powerful it is in the convergence of series. Series is kind of how I started off this little bit on sequence and series, and some fun with series. And series are really, really useful tools because it's what we're going to end up defining integration through. So we're going to prove, or in one case disprove, the convergence of a series, and we're going to use, in one of them, we're going to use the monotone convergence theorem, which is what I wrote as theorem 4, and in the other one, we're going to use our little, where was it? Theorem 1, our all convergent sequences are bounded. Okay, so the first one we're going to look at, a crucial sequence, very, very famous. It's the sequence S of n is equal to 1 over n squared. Now, if you've looked at YouTube at any point, you'll know that this converges to pi squared on 6. But we're not going to prove that it converges to pi squared on 6. We're just going to prove that it converges, which is easier to do. So we're going to just prove that it converges, which is quite a lot easier to do than actually proving it converges to pi squared on 6, but we're going to just sort of test the machinery that we've developed. So for starters, let's just write out a particular S of n being equal to, 1 over 1 times 1 plus 1 over 2 times 2 plus 1 over 3 times 3 plus so on up to 1 over n times n. We know that that thing is less than 1 plus 1 over 2 times 1 plus 1 over 3 times 2 plus 1 over 4 times 3, so on, up to 1 over n outside of n minus 1. Right? So we're just, in each case, decreasing one of them by 1. And because it's on the denominator, that means our thing has increased and hence is larger. We can rewrite that a little bit. That thing is equal to 1 plus, where am I? 1 plus 1 minus a half, plus, 1 half minus a third. Just going to make sure I get this right. Yeah. Plus like a third minus a quarter, plus ... plus 1 over n minus 1 minus 1 over n. Hopefully you can see that that's just basic algebra, even though I nearly stuffed it up. Which we can then clearly see that this sequence telescopes. And now, in case you were a little confused, we're allowed to group this. We sort of talked about last video how grouping and stuff doesn't really work. We're allowed to group this because it's finite. We're going to talk about infinity later, but for the moment we're allowed to group it because it's finite, and we end up with that thing being equal to 2 minus 1 over m, which is of course less than 2 because m, what is that? N, because n is positive. So we've proven that S of n is bounded. It's most definitely less than 2, so it's bounded. It's also increasing because we're adding something to it each term. So it's monotone because it's increasing, and it's bounded, which means it has to converge. So we've proven that this this sequence converges, which is it's fantastic. It's exactly what we wanted to do. I'd just like to point out, because I didn't make it very clear before, this is a sequence, S of n, so it's the sum of the terms, obviously. And what we've really got going on here is this partial sum. So it would have perhaps been a wiser idea for me to call this, partial sub n. Potentially a bad choice of notation, so I apologize for that. The next example that we want to do it's a bad choice of notation, so I apologize for that. It's potentially a bad choice of notation, so I apologize for that. And that was really quite easy to do. That was, 4 or 5 lines. And we managed to prove that some sequence converged, series converged, some series that otherwise would have potentially been quite difficult to prove the convergence of. We managed to do that through the Monotone Convergence Theorem. It is a very powerful theorem. The next thing we're going to look at is using our other theorem, our theorem number 1, this all convergent sequences are bounded, to prove that a particular sequence doesn't converge. Another very famous example, which is the Harmonic Series. And that's the one that is generated by the sequence of numbers 1 over n. So I'll write out, our partial sums are, 1 plus a half plus a third, so on to 1 over n. And now we're going to look at, rather than just looking at p sub n, we're actually going to look at a specific subgroup of our partial sums. We're going to look at the subgroup which are powers of 2. And the reason that it's okay to do this, or at least in our specific case, is because if a subsequence or a subset of our partial sums doesn't converge, then it can't be possible for the entire sequence to converge. And what I mean by like a subset is I don't mean the first 4, because that's not fair. I mean an infinite set, but that's a subset. Okay, so basically just writing what I have above. So on and so forth, up to 1 over 2 to the n. Well, we know, or what we can do, is we can prove that this thing is greater than 1 plus, a half. And if I go from a third, so rather than having a third, if I have a quarter, because a quarter is less than a third, last I checked, if I rewrite a quarter and a fifth, if I rewrite a third and a quarter as both being a quarter, that's fine. I'm still dealing with something which is now smaller than it. But now I'm onto a fifth, so I can no longer write that as a quarter, so I'll write the next few as an eighth, or I'll write the next 4 as an eighth. And I think you get the idea, up to 1 over 2 to the n plus 1 over 2 to the n. And that is the reason why we chose the power of 2. I think it should be pretty easy to see the pattern here. We've got 1 plus a half plus, well, that thing is a half, an eighth plus an eighth plus an eighth plus an eighth. That's 4/8, which is a half, so on and so forth. That last thing also ends up being a half. And we've got n lots of these. So that's going to be equal to 1 plus n times a half. N lots of them are n minus 1 lots of them. I can't really be bothered. My notes might be wrong, but I've got n lots of them written there. So we've shown that our sequence, or the partial sums, our series of partial sums is larger than this. And now remember how n in our series of partial sums can go arbitrarily big? That means 1 plus n over 2 can also get arbitrarily big, which means that our partial sums aren't bounded. And by our theorem that all convergent sequences are bounded, that means that this sequence can't converge. The harmonic series with the sequence of partial sums doesn't converge, which is, it's a powerful result, because you add up the first 100 of them and you're not really at a very big number. It's kind of crazy that it doesn't converge, and it's one of those ones that when you first see it you think for sure that converges, and it doesn't end up converging. We've managed to prove it not using calculus. We've managed to prove it just using basic ideas of rearranging finite sequences, and that's the big key bit, finite sequences, because we'll look at trying to rearrange infinite sequences, and this harmonic series pops up again because it's quite interesting. That's exactly what we wanted to do, and those two examples sort of finish what I wanted to talk about today. Now I'd like to finish up this little bit about sequences and series in the next video, because it would be great to spend a whole bunch more time on it. There's so many things you can talk about, ratio tests, able tests, infinite products. There's a bunch of great stuff in sequence and series. But with following what the book does and being conscious that this is sort of an introductory course, just getting you used to it, what we're going to do is just talk about next week the Cauchy creation and the Bolzano-Weierstrass, or however you say it, Weierstrass, or whatever, theorem, which are two very, very, very powerful theorems, and they'll allow us to sort of look back at our axiom of completeness and talk about, is that really the only axiom we could have chosen? Could we have chosen something else to be an axiom? And then in that, after we talk about the Cauchy creation and the Bolzano-Weierstrass theorem, I'd like to answer the question I posed last time and figure out, in infinite sequences, when can we rearrange terms? And is there a rule for that? And in fact, there is, and it's very interesting. But we'll need to set up those two things before we do that. But that will all be done in the one video, and then we'll be able to move on. I think the next thing the book does that we're following, that's Abbott's second edition, Introduction to Analysis, I think, is it talks about basic topology. I'm not entirely sure if we're going to do that yet. I'll have a quick read through how he does it and see if it's worthwhile. If I recall, it has been a little while since I've read the book the first time, but if I recall, it is quite valuable. So I think we'll do a little bit about that before, moving on to some other things. But what we've got here, and by the end of next week, is a very powerful set of tools to prove the convergence of sequences, or at least a very well-defined set of tools to prove the convergence of sequences. I would just like to highlight briefly a little thing that I didn't mention before. Right here, when I was proving the monotone convergence theorem, we proved that it was less than the supremum. And that was assuming that the set had a supremum. We could only do that because of the axiom of completeness. And it's kind of hinting towards next week when we discuss the axiom of completeness again. Which, because the real numbers are defined with the axiom of completeness, that means this theorem, well, at least in the form we're presenting it, only holds on the real numbers. So I thought that was very interesting because it's just sort of demonstrating that what we did previously wasn't a waste of time. Setting up the real numbers the way we did is very beneficial. But yeah, thank you.